Good morning, I'm Michelle Sanner, and today we are going to be talking about how to draw chemical structures, how to take a chemical formula and turn it into a two-dimensional arrangement of bonds. And we do that using something called a Lewis structure. So there's a couple of steps to drawing an accurate Lewis structure, and first we're going to talk about define exactly what that is. So a Lewis structure is a formula in which your atomic symbols represent nuclei. For example, you would draw, if you were drawing carbon, you would draw a C because carbon is its atomic, an element symbol on the periodic table there. That represents the nucleus of carbon and all of its inner shell electrons, its core electrons, for example. Then we use dots to represent the valence electrons and dashes to represent bonds. So a single bond may look like a dash, like this. There may be instances where we need to add double and triple bonds, and so you will just simply add more dashes. A double bond is represented by 2 dashes, a triple bond represented by 3 dashes. And all the electrons are represented by little dots like this. Here is an example of a Lewis structure. We've got water. So we are showing hydrogen's nucleus is indicated by an H. That's its symbol on the periodic table. This represents the nucleus of hydrogen, and this does as well. Over here we have oxygen, representing the nucleus of oxygen and its core electrons. And then oxygen's paired electrons that are not participating in bonding are up here at the top, and the electrons that are participating in bonding are implied by this dash here, this dash representing a covalent bond. So Lewis structures, what they do is allow us to predict the structure of a molecule and the number and types of bonds present. To draw a Lewis structure, just follow these steps. So first you want to identify the number of each type of atom that's in your molecule, and we'll do that with the chemical formula. So here's the chemical formula. We have 1 phosphorus. It's implied because 1s are not written in the formulas. So I'll need to include 1 phosphorus and 3 atoms of chlorine here. In general, we place the least electronegative element in the center of the arrangement, unless of course it's hydrogen, which is low in electronegativity, but it only has 1 electron to participate in bonding, so it's not able to accept multiple bonds. So hydrogen stay on the outside. We put the least electronegative element in the center, and we arrange the rest of the elements around the outside. So if I check on the periodic table and I compare phosphorus here at number 15 to chlorine, I could see that chlorine is further to the right on the periodic table. It's on this trend is that electronegativity increases as we move across. So chlorine is more electronegative, phosphorus is less. So I will go ahead and place phosphorus in the center. And then I'll arrange those 3 chlorines around it. Just start at the top, chlorine, the side, and the bottom like that. The next step is to draw the electron dot configuration for each of these atoms. So remember, the electron dot configuration simply takes the number of valence electrons that each of these elements has and arranges them clockwise around. I can see that phosphorus is in the 5 valence electron column and chlorine is in the 7 valence electron column. So I'll bring that over with me as I draw them. So starting at the top and working my way around, I have 1, 2, 3, 4, 5 valence electrons on phosphorus. On chlorine, I start at the top, 1, 2, 3, 4, 5, 6, 7 valence electrons on chlorine. And remember, I always start and add the single electrons on all 4 sides before I go back and add the second electron. That's an important notation thing to note. 4, 5, 6, 7. So we've done number 1, we've done number 2, we've done step number 3. Check. The 4th step is to draw a line from any unpaired electrons, so any lone electrons on the outside atoms. We're going to draw a line and join them up with unpaired electrons on the central atoms, and this will represent a bond. So I will take a different color here and look for, here is an electron by itself on phosphorus, and I'll connect it to this lone electron on chlorine. I see this phosphorus has a lone electron on the bottom, so I'll connect it to this lone electron on chlorine. I'll do the same thing here. There we go. Now this looks kind of ugly, so I can clean it up and rearrange the electrons so that everything is neatly squared off, and that indeed is the next step. Step 5, clean up the structure so that the lines representing the bonds are straight. I'll just bring all my work here down into the next step. So I have a phosphorus in the center, bonded to a chlorine, bonded to a chlorine, bonded to a chlorine. I cannot forget to bring my pairs of electrons. So bring the same number of electron pairs that you had in the last step and just kind of neatly square off that molecule. So we cleaned up the structure to make sure that the lines representing bonds are straight. The next step is to kind of check and make sure that this is satisfying the octet rule as much as possible. So what I've written here is connect any additional unpaired electrons if needed. In this case, we don't need to form double and triple bonds. And we'll do an example of that a little bit later on today. Number 5 is count the number of electrons, including the ones in bonds, and try to ensure that each atom has a full octet of valence electrons for maximum stability. And don't forget to keep in mind this idea that hydrogen is stable with only 2 valence electrons. Every electron needs to either be in a pair or in a bond to be a valid Lewis structure. You don't want any lonely electrons. So let's see how close we are to the octet rule. All right, let's start with phosphorus. I have 2 electrons here, not participating in bond. Remember that each bond really represents 2 electrons that are shared. So I have 2 electrons there, there, and there. So I have a total of 8 valence electrons surrounding phosphorus. That's a full octet, so that's a good configuration for phosphorus to have. Looking at each of the chlorines, I can see that it has 2 participating in the bond, 2, 2, and 2. So once again, a full octet. So this is probably the best Lewis structure for this molecule because it ensures that each atom has a full octet. This won't always be the case, but you want to try to maximize stability whenever you can. And remember, the reason things form bonds is because in doing so, they can share electrons in order to gain stability and gain that full octet. Let's practice. So we'll draw the Lewis structure for this molecule. Let's write down what it is that we have. We have an implied 1 beryllium atom and 2 fluorine atoms. I want to decide which is the least electronegative and then arrange the rest of the atoms around it. So I'll go to the periodic table and look for beryllium. Here it is, towards the left, fluorine, way over here to the right. So certainly beryllium is going to be the least electronegative. I can also see while I'm here that it has 2 valence electrons and fluorine has 7. So I'll bring that over with me. Beryllium will be placed in the center as the least electronegative element, and I'll just put arranged fluorines on either side. Now it's time to draw the electrons. Beryllium had 2, 1, 2, and fluorine has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. Now it's time to join up those unpaired electrons. So any electron that is single all alone by itself on one of the 4 sides needs to be joined from the outer to the central atom. So I see an unpaired electron on fluorine, I'll bond it there to beryllium. And way over here on the left is an unpaired electron that I can bond here as well. Now clean up this structure. Beryllium, bonded to fluorine, bonded to fluorine, and don't forget all these electron pairs. Those have to come with you every time. So you want to end up with the same amount of electrons that you started with. Great, it's time for an octet check. I can see that each fluorine has 2, 4, 6, 8. Remember, there's 2 electrons in every bond. So a nice 8 stable valence electron configuration for fluorine. Beryllium, on the other hand, only has 2, 4. But this other fluorine has 8 as well. So we've done our best to maximize stability here. So it's acceptable to leave the Lewis structure as is, even though beryllium only has 4 valence electrons. So this is a good Lewis structure. We've maximized the octet in 2 out of the 3 atoms. Let's try another one. See if you can pause the video and try this on your own using the periodic table. How would you arrange boron with 3 chlorines? Don't forget to put the least electronegative species in the center and the most electronegative arranged on all 4 sides around. Clean up the structure, match up the non-paired electrons, and we'll see what you get. So how did you do? Were you able to form 3 bonds with boron in the center, extending out to 3 separate chlorines? Did you remember to bring all of the non-bonding electron pairs? If you did, great. And now it's time to look at our octets. Well, I see that chlorine has 2, 4, 6, and 8 total electrons, giving it a full octet. So nice and stable on each of these chlorines. Boron, on the other hand, 2, 4, only 6 valence electrons, but we've done our best to maximize and obey that octet rule for as many atoms as possible. So I would consider this a valid Lewis structure. Try another one and see if you can arrange chlorine, 4 chlorines, around a central carbon atom. We'd put carbon in the middle because it's the least electronegative species. Pause the video and see if you can come up with what I do. So how'd you do? Were you able to find 4 valence electrons on carbon? They very neatly form bonds with all 4 chlorines around either side of that carbon. Don't forget to bring over your valence electrons. And what I love about this structure here is that every single atom has a full octet of 8 valence electrons, including carbon, because don't forget that this dash really represents 2 shared electrons on each bond. So 2, 4, 6, and 8 valence electrons. This is a valid Lewis structure. Now, we may have situations in which we are drawing the Lewis structure of an ion. Remember, an ion is a charged species. It either has more protons than electrons or more electrons than protons. And so that makes the element or the molecule overall not neutral. It ends up having a charge. So when we draw Lewis structures for ions, we cannot change the number of protons. If we tried to adjust the number of protons, we would end up changing the very elements themselves because elements are defined by their number of protons. But we can manipulate the number of electrons. We can add and remove electrons. So let's take a look at this molecule here. I have 1 boron and 2 hydrogen. I also have a negative sign, an extra negative sign. That means it's 1 negative. So it has 1 more negative particle than it does positive particles. And of course, negative particles are electrons. So I need to make sure I include 1 electron in my Lewis structure. And I'm going to sit on that for a moment and wait until I need it. So let's figure out the number of valence electrons. We have boron here with 3 valence electrons, hydrogen here with 1 valence electron. I will place boron in the center because remember, hydrogen is always placed around the outside. And I'll just put my 1, 2 hydrogens there. Time to add my 1, 2, 3 electrons on boron and my 1 electron on each hydrogen. So I've taken care of this, I've taken care of this. I still have this electron to go, but I'm going to wait for just another moment and make as many pairs as I can, as many bonds as I can first. All right, and what I see here is 1 lone electron. And one of the rules of Lewis structures is we're trying to avoid lone electrons. Luckily, this is an ion, so it has an extra electron that I can bring down and add right there, making a nice even pair. So cleaning the structure up, boron bonded to 2 hydrogens and 2 electrons in a pair on one side of boron there. So that's why we do ions. You can't change the number of protons, but you can add and remove electrons in order to make all of your electrons have nice even pairs. Let's try a positive ion, NO2. So I'm going to have one N, two O's, and then in this case, I'm not adding an electron. In order to make this species positive, I need to remove an electron. So I'll make a note to myself that in this step, I'm going to remove an electron. Let's go ahead and decide which goes in the center. I'm looking for the least electronegative species in the center, and I need to arrange those two oxygens around it. Now I'm going to go look at the periodic table and see how many valence electrons each has. Nitrogen has 5, oxygen will have 6. Starting at the top, working my way around clockwise, 1, 2, 3, 4, 5. Here goes oxygen, 1, 2, 3, 4, 5, and 6. And another oxygen, 1, 2, 3, 4, 5, and 6. I'm going to go ahead and start trying to make some electron pairs here. I see a lonely electron here that I'm going to match up. I see a lonely electron right here that I'm going to match up. And oh, isn't this interesting? I have a couple of leftover lone electrons. Before I go and remove one of these electrons, I'm going to go ahead and make a double bond. So this is a great situation where I can form a double bond. I'll do that by just going ahead and forming a bond between these two lone electrons on nitrogen and oxygen. Now, I'm still left with this idea of needing to remove an electron. So I'm looking for any electrons that are left over, any that aren't going to be able to form a pair. And I see one right here. So I'm just going to cancel out and remove that one electron. So I've taken care of each of these steps, and I'm ready to clean up my structure. N bonded to O, bonded to another O. Don't forget to bring your pairs of electrons. You can rearrange them, that's fine. And don't forget, oxygen's going to have 2 pairs, so I'll bring those with me. 2 pairs on this oxygen, bring those with me. And I'm done. I have a valid Lewis structure. I've maximized the number of atoms that have a full octet. Nitrogen has 2, 4, 6, and 8. Don't forget this double bond is really 4 electrons. 2 pairs of electrons being shared, one in this bond and another pair in this bond. So nitrogen has a full octet. This oxygen also has a full octet, 2, 4, 6, 8 electrons there. And this oxygen over here has 6 valence electrons. So we've done our best to maximize the number of valence electrons on most of the atoms, and it's okay if one of them ends up not being completely full in its valence shell. So that is a little bit about how to draw Lewis structures. The next time we meet, we are going to practice a lot of these. You'll be responsible, of course, for being able to draw the structure of a neutral atom as well as an ion that's either positive or a negative. I hope you're doing well, and I'll see you soon. Have a great day.